first off, this is not just the work of myself, but actually a couple of different large consortiums. So we have this DJ for Earth collaboration, where we actually just recently got a paper published at the Journal of Atmospheric Modeling, as well as a even larger consortium of folks where we had a recent submission to the Gordon Bell for Climate Science. Hopefully it gets to the next round. Nevertheless, like at this point, I think there's like more than 50 people across basically every continent, from academia, national labs, industry, and sort of beyond. To sort of begin with, I want to introduce a couple of the sort of key challenges that at least I see when doing sort of modern Earth systems modeling. So the first of which is scale. So these types of simulations are extremely big and detailed. And by detail, I mean in both the sort of resolution. So we have consequently like a grid, and as we increase the resolution, the number of grid points grows quite large. So we have this axis, but we also sort of have a feature axis as well. We want to have an increasing complexity of the actual simulations that we want to do. Regardless of the sort of source of that detail, this creates vast amounts of output. As an example, for some amounts of simulations like this CMP6, we have like 10 petabytes of outputs. If you're just to look at, say, like an Arctic simulation, not even the sort of like whole world, at 1 to 2 kilometer resolution, that takes 7 million core hours, creates another petabyte of output, and runs on 10,000 cores. And I will note that 1 to 2 kilometer output is it's nice, but people nowadays are trying to do like 200 meter output, and obviously that goes up by the square plus. Another sort of interesting thing that I'll note here, which is useful for potential future data layouts we may want to exploit. I usually see this as sort of like a pancake Earth. So we have this image here on the top, where we have like an x-axis and a y-axis, sort of like going around the globe for this ocean. But the z-axis, the surface of the Earth, even the atmosphere of the ocean, isn't nearly as big as the entire circumference of the Earth. So we have this simultaneous notion that 2 of these axes are a lot more important than this other axis in practice. We also have a challenge which is fundamentally that of the data itself. So here, I have shown a bunch of sensors off the coast of Japan. So it turned out, very unfortunately, there was a tsunami back in, I think, 2011 that took out a nuclear power plant. And this was quite bad. And people wanted to figure out a good way to have like an early warning system for these types of things in the future. So they put out like a bunch of buoys all across the coast of Japan to sort of measure exactly the sort of relative shift to the size of the ocean. Again, I'm not an oceanographer myself. I'm a compiler person, but to collect a myriad of different pieces of data such that they could be sort of reconstructed on the back end and go ahead and predict what is the likely sort of tsunami, give some amount of an early warning. But you'll note here, this doesn't cover the entire surface. It basically follows what is reasonable to sort of put out both within a budget as well as sort of physical constraints of what we can do. There's actually a really fantastic paper that won the last year's Gordon Bell Prize at using some amount of sort of inverse modeling to figure out where to sort of put some of these pieces, as well as do some amount of early tsunami prediction. The third sort of these big challenges is the models themselves. So at a very high level here, I'm going to go ahead and describe how I see these models working. So first we have some initial conditions. So I'm going to initialize that state of the ocean and the lakes to whatever pieces of data that I have. Either maybe I got it from the earlier pieces of data, or I fill it in with some sort of approximation. I go ahead and from there, I want to go run some simulation on top of it. For some of these pieces, I know what I want to run. I have some physical equations, but it also turns out that in the real world, we don't know the physical equation we want to run for all of these pieces. Sometimes it's just parameterized, so we need to go figure out what the right parameter on top of a Taylor series or whatever else is. Other times, we don't even know what the right equation is, so we need to go ahead and figure this out. This combines itself with the idea that there's also boundary conditions. Like I go ahead and I might want to sort of like have a cyclic boundary condition, or I might have something going ahead and touching the various continents or the lakes. Nevertheless, the big sort of takeaways here is for all of these individual pieces, there's a lot of stuff we don't know. We don't know exactly the initial conditions. We don't know exactly the insides of those parameters, let alone the equations themselves. And we have all these other sort of different types of things that influence the actual simulation themselves. It turns out that there's a couple of nice things that people can go ahead and use to sort of predict and resolve some of these uncertainties. Differentiability is one of these big, heavy-hitting tools. It enables powerful algorithms to go ahead and analyze these models, in particular to compute inverse problems. You can differentiate with respect to that boundary condition. You can explore the forcing sensitivities. You can differentiate with respect to those initial conditions. You can predict a forecast, differentiate with respect to those parameters, try to calibrate to the data, or even import that sort of sparse data, and even potentially go ahead and compute surrogate models. Finally, the last big challenge inside of these real-world system models are the code. There's a lot of really big code bases out there. Like MIT GCM, I earlier today went ahead and did like a source line of code check. It's 800,000 lines of Fortran, roughly. These are big codes developed by entire institutions like DOE, NASA, Max Planck, and the likes. They're made by experts in the scientific side of simulation, not as much experts on the computational front, though they do employ a lot of people who are experts in computer science as well. And what this means is that sweeping changes are hard. There's a story like a couple of decades ago, and I might be getting some of the individual pieces of it wrong, when I think it was MIT GCM wanted to go add differentiability. And it turns out differentiability, very useful as I showed earlier, but also very invasive. They had to have a second copy of each one of their individual functions, that if someone changed the original function, they also need to make sure that they maintain that second differentiable form of it. And it turns out that making sure to maintain twice the amount of code for nice algorithms that you can do is very hard. So they eventually dropped it because that added maintenance burden stopped them from doing the science they actually wanted to do initially, and it wasn't worth it to them at the time. Nevertheless, we have these 4 big challenges. We have scale, we have data, we have models, we have code. We want to go ahead and run these things. So how can we actually fix these challenges? How can we make them work? What I'm going to claim here is we want to actually go ahead and combine the domain scientists with the computational and computer scientists. But we want to go one step further. We want to ideally build a compiler to automate that sort of computational burden that otherwise is potentially plaguing the ability of these systems to move forward. I'm going to primarily talk about this in the context of 2 different things. I'm going to talk about this in the context of differentiability, in the context of performance portability. This is applicable to many other regimes as well, that ideally we want to build compilers to go ahead and integrate in. So differentiability, derivatives are fantastic tools. They're really key to both science and machine learning. If you're a science person, is the context of this workshop here, it's useful for uncertainty quantification, any differential equation, and even sort of computing the floating point errors inside of your program. If you're an ML person, you've probably trained a neural network or seen Bayesian inference or a lot of these other sort of things. And these are all examples across different scientific domains of algorithms that require differentiation. What's really cool is these derivatives can be generated automatically from code. So I here have this simple ReLU3 function. I can perform a derivative and have this new function here on the right, which computes the corresponding derivative of it. Instead of having x cubed on that branch, I now have 3x squared. And unlike numerical approaches, automatic differentiation has a lot of nice advantages. First of all, if I were to numerically approximate it, I could say f prime of x is approximately f of x plus epsilon minus f of x for some epsilon. Of course, the real derivative is the limit as epsilon approaches 0. So if I have epsilon any bit non-zero, even 10 to the minus 200 or whatever else, I'm going to get some amount of theoretical error because it's not exactly 0. Very unfortunately, I also get numerical error from the other side. If epsilon is really small, then f of x plus epsilon is very close to f of x, which means it might only differ in the last bit, or perhaps not even any bits, which means that we have both of these sort of regimes causing numerical errors from different directions. Even worse, let alone the numeric sort of error, there's also a performance question here. If I'm going to compute this and I want to compute the gradient oftentimes, so that's the derivative with respect to all inputs, I need to iterate through all of my inputs and then do this relative subtraction. One of the nice advantages about automatic differentiation is we can ignore these sources of numerical error, because like we see on the top, we're computing the equation itself. And also we can compute the entire gradient in one sweep. We don't have to do it for all of these individual inputs. Now, again, derivatives, really useful, but they're also very costly, and some of the most difficult to use algorithms, as we saw earlier. So I also work very closely with the folks who make these pretty pictures of black holes that get on all the newspapers. This particular one took roughly a week on a cluster to go ahead and run. Majority of runtime is inside of the derivative, computing Bayesian inference. Fortunately, we were able to take this derivative time down to 1 hour on a single thread. And as I'll sort of joke, you give the computational science all these wonderful speedups, and it's really a currency that they used to do even more and bigger computational science with the original budget that they had. Same thing sort of applies here. There's a lot of different approaches that people have done in the past. There's, design a new domain-specific language. Now, this is great if your new DSL matches exactly the types of things that you want to do. So if you're a machine learning person, go write it in, TensorFlow or PyTorch. If you're a graphics person, put it inside of Tachi. Now, if it doesn't match, you have a little bit of a problem. First of all, it may not be able to run, or it runs really slow. So here we have the ReLU3 function. TensorFlow doesn't really like the idea of conditionals. It turns out you can sort of shove it inside of these lambda capture expressions, but it's not going to work out terribly great. Second approach is known as operator overloading. So inside of an entirely new DSL, I'm going to have a differentiable version of specific language constructs. Inside of C++, there's a tool called Adept. Instead of having my regular doubles, I have differentiable or adjoint A doubles. Inside of Python, there's a tool called JAX. Instead of calling numpy.sum, I'm going to call jax.numpy.sum for everything. We can go ahead and rewrite our code. Now it's going to take the templated version, so we take any type of double. If I want to go ahead and execute it, what actually happens is at this first x is greater than 0, I'm going to log the fact that I computed x is greater than 0. Then in the second version, when I compute pow, I'm going to log the fact that I computed pow. Then in my stack of instructions, I'm going to go ahead and one by one reverse interpret and compute the derivative of all the different things that I've seen. Now, this works, but it comes with a caveat. Interpreting instructions is a lot slower than directly executing instructions. Also, if we have a for loop here, and we just add a bunch of things inside of our stack, we now no longer have the for loop. We have just a giant set of all these sort of pieces. Third approach is known as source rewriting. Instead of making a new language or a new subset of a language, I want to take the existing code. I want to rewrite it and have it spit out new source code for me. There's a state-of-the-art tool for this called Tapenade. It's primarily in Fortran, but it also works inside of C. We take in ReLU3 goal. I want to spit out new grad ReLU3 as an individual function. Looks great. Looks like what I'd go ahead and directly execute. Equally comes with a caveat. That tool inside the middle needs to understand the entirety of the program semantics of the language given to it. And it turns out that the C++ language specification is very long. It's hundreds of pages. Nobody should read it, and most compilers even don't fully implement it, let alone an extra tool. So if you have pointers, you have templates, you have structs, you have any of these sort of things that aren't even terribly crazy in the context, these tools often don't fully implement it, and then you're sort of yet again stuck in being able to not differentiate. But when it works great. All of these, independent of your favorite, because they all come with their own sets of pros and cons, follow the same general idea. I have source code in my favorite language. I spit it through an AD tool in my favorite language. I get new source code in that language. Then I run the compiler. And I run compiler optimizations, and I execute the final code. We can now look at how this actually works in practice. So when I was actually in undergrad, I was both a physics major and a CS major. So I spent all of my time normalizing vectors for fun. And I wrote this here as a physics major. So here we go ahead, magnitude costs O of n. This normalized function, though, costs O of n squared, because I compute magnitude inside the loop every iteration. Fortunate for freshman me, compilers exist, and they can figure out that we can move the magnitude function outside the loop, bringing down the total runtime to now just O of n. Now, if we want to differentiate this code, it basically involves running it backwards. So if I take the faster version of the code, I run the faster version of this backwards. I have grad mag outside the loop to begin with. Or I have regular mag outside the loop to begin with. I have grad mag in the derivative loop outside to begin with. Also runs in O of n. That's not how those existing tools work. Existing tools work the other direction. We have mag inside the loop because we didn't run the optimization yet. We perform differentiation. We have grad mag also inside the loop. We can run, once again, loop invariant code motion, try to fix it up in post, but we get stuck. This, variable dres is defined in the loop. It's used in that grad mag. We can't hoist it outside. And the key idea here is if we can move differentiation to happen after optimization and combine with it, at least in this case, we can create asymptotically faster gradients and hopefully practically faster ones as well. And that's exactly what we're able to do. So we built Enzyme. It works on the compiler representation. In the first iteration, it works on LLVM. It now also works on MLIR. And whatever your favorite IR sort of is, gives a couple of key benefits. One, we don't really care what source code language that you use. The production Clang, the production whatever else already emits all that front-end lowering for us. So we don't really need to care if the language spec isn't supported. We just need to implement differentiation on that internal level. And notably, we can combine with optimization as well, hopefully getting a little bit better performance and going to our favorite set of devices. As a quick example of how this works, I have that ReLU3 function. I have this enzyme autodiff, which is a magic function. In the LLVM world, the code appears here on the right. I have the branch. If I'm going to go ahead and execute it, conditionally execute pow, and if not, go ahead and have the final return. I first run an analysis known as activity analysis. I want to figure out which of the variables are important to differentiation and which ones are not. This is useful for two reasons. First of all, if I can avoid differentiating instruction that doesn't actually matter to the overall code, I save a lot of time. The second reason is, we saw earlier that the derivative of x cubed is 3x squared. Basic calculus. Can anyone here tell me what the derivative of thread ID is? Excellent. Yes. Yeah. Perfect from AP Calculus. Yeah. There's no really well-defined derivative. So we want to avoid taking derivatives of things that don't make sense either. And we run a whole analysis to figure out which we need to take derivatives of. For each of those original variables, we're going to allocate in zero what's referred to as shadow memory, so like space to store the derivative. And then for each one of those differentiable instructions, we're going to go ahead and compute what's referred to as an adjoint, or basically, we're going to increment the derivative by the partial. So in this case, increment it by 3x squared. We do this for all of the partial derivatives in our entire program. We get the total derivative. We successfully compute the entirety of the expression we care about. We can, of course, run optimizations in post, and we get something that looks relatively nice. And we're going to stop looking at LLVM now, and we get the equivalent to the high-level source code that I would have wanted to begin with. We can go ahead and run this on a bunch of applications, and we did this for our first paper at NeurIPS back in 2020 on both some scientific code as well as some machine learning code. And the sort of key idea we wanted to check here is how much of an impact does moving that differentiation to run after optimization actually matter? So in this enzyme and reference pipeline, in blue and orange respectively, they both run the same tool we have called enzyme, except for the enzyme pipeline, we run optimization first, whereas for the reference pipeline, we run differentiation immediately first to emulate as if it was implemented at the source code, just in case there's any differences in implementation between our tool and another tool. And that ablation test alone showed that moving differentiation got you a 4.2x speed up compared to not moving the differentiation procedure. Now that's very fun, but let's get back to climate science. So here we go ahead, and we want to go solve some interesting problems. So here we have what's referred to as the sort of shallow water equations. Effectively, it's a partial differential equation that describes basically Navier-Stokes. You start at some initial condition, you iterate forwards in time, and you time evolve it. And specifically here, we want to perform a sensitivity analysis. So how does some quantity change if I perturb the field? That particular quantity here represents kinetic energy based off of the individual momentums. I won't dive too much into the physics, but I promise we go run this and we get pretty pictures like shown here to compute the relative change of the sort of like logical quantity of interest with respect to the things we actually care about. That comes with some caveats though. Like I mentioned, we iterate this thing through time. So here is a very simplified version of iterating something through time. We might need to save data from each one of our forward iterations to be able to compute the corresponding derivative. If we're very lazy, we just save every single iteration, and then the amount of data we need to store is going to be proportional to the total number of iterations. This can quickly blow up, especially if you want to have a long time horizon running evaluation. And there's a lot of techniques known as checkpointing that try to perform algorithms to reduce this. Here I have a very simplified version of this, where effectively we save every few iterations. And in the backwards pass, we just continue forwards a little bit from there. This is extremely useful in the climate science domain, and actually an active area of research right now of figuring out how we can reduce this memory burden, because when you want to run big computations, you also want to run a really long time, usually. Turning on versus off checkpointing for the memory obviously changes the asymptotic behavior. So in blue, we have it relatively flat with respect to the original simulation versus just blowing up. But it doesn't also just impact memory, it also impacts the overall runtime, because if you're going to have to save and load and store more into memory, that takes time. So potentially counterintuitively, this saves both memory and execution time by performing checkpointing, at least in this case here. The second big problem that I alluded to is differentiation is useful, but also there's been a lot of trends in computing hardware recently. Here, I just screenshot a bunch of examples from, Meta, from Anthropic, from AWS, from Google, all saying they have the latest and greatest AI chip, which is very fun. But these AI chips are not designed for existing code, let alone the sort of scientific computing or sort of even more general, specifically the like climate modeling that we want to do. They're designed to speed up the AI models. And in fact, they claim, at least Google does here, that there's more than 24 times the amount of computation in a single pod of TPUs than is available in the largest supercomputer in the world. Now that's great if you're an AI practitioner, but how do I access these chips? And for just ease, I'm going to put an asterisk here and write all of these as TPUs. Google was the first to really create one of these tensor accelerators. They called it a TPU. Everyone else has their own name for this. You have like tensor cores on GPUs. You have like Mida from like Meta and whatever else. I'm just going to call them all TPUs and put an asterisk on it. And scientists, unfortunately, do not write code which is friendly to these TPUs. Here's an example snippet from MFEM, which is actually what was used in that Gordon Bell run earlier, not our Gordon Bell run, but the one for the tsunamis, as an example. MFEM, once again, like the other climate models that we were talking about earlier, is also very big, hundreds of thousands of lines of code. It's templated. It's, most importantly, not inside of Python to be able to make this go ahead and run there. It's sometimes in CUDA. But if we look more deeply at some of the scientific code, and specifically if we look more deeply at the types of code inside of climate models, there's actually a lot of structure here. So here's how, from a state-of-the-art model called Oceanigans, implements all of their sort of like, forward models inside of Julia. It looks like just a bunch of generic CUDA kernels. I'll save you the Julia syntax, but we call this arbitrary kernel twice. If we step back a little bit and we squint at what that kernel is actually doing, it's basically running a convolution across the entirety of it. And this is actually extremely interesting because those AI chips were first designed and implemented back in 2017. And if you look at AI in 2017, convolutional neural networks were all the rage. And it really does take a long time to go tape out chips and send them off to the fabs. Fortunately for all the AI folks, those convolutions are actually, if you build a good convolution machine, it's also usually a good matmul machine. And that same matmul is exactly the sort of process inside of the big sort of transformers that we go ahead and run. But in a little bit of an odd change of fate, the very sort of accelerators designed to go ahead and speed up AI actually, could be argued to be even better for the scientific codes here that we care about, if only we could get them onto those chips. So that's exactly what we went ahead and we aimed to do. So we built a framer that was designed to take existing code, in particular in this case, existing CUDA code, as emitted by your favorite compiler into LLVM, and raise it up to the high-level tensor instructions that are available within these chips. So we go in multiple stages. We first have our front end. In this case, on the right, we show Julia. It emits LLVM code. We raise it up to a high-level form that has generic forms of the parallelism. I'm skipping over a couple of the details. From the high-level form of parallelism, we turn it into high-level tensor instructions, perhaps not the fastest tensor instructions, but one that at least run. And then we go ahead and optimize those tensor instructions to make it one that we actually do want to execute. And notably, from here, we're able to take a single node version of the CUDA code, which is even better, because then the sort of domain scientist doesn't need to think about how to distribute their workload across these individual pieces, and automatically synthesize a distributed either GPU or distributed TPU or your favorite version of the program. So we work in several in several steps. So we start off with the original LLVM code is imported now into MLAR. We detect the high-level structure that this represents, mathematically an absolute value, that this represents not just, an individual sort of go-to style block, but a while loop. From there, it represents a for loop. From there, it represents an affine or sort of known memory accesses inside of the for loop. All that's very fun. That's covered in some earlier papers we have on a tool called Polygeist, published at CGO and PPOP a couple of years back. I'm going to focus on this last step here, which is how do we get that final piece to the tensor instruction set? How do we get from there to stable HLO? It turns out that representing your program as a sort of permissive or device-agnostic form of parallelism is incredibly powerful. And again, if you're interested in more details on this, email me and I'll forward you the relevant papers. But we've now raised this to a form that we have a generic parallel for that doesn't care about what device and just says it is legal to run in parallel, not that it is required to run in parallel. So one way we can go ahead and execute this parallel loop is we can run iteration 1 fully, then iteration 2, or maybe even iteration 2 fully, then iteration 1. We can also interleave the individual instructions inside of this loop. So we could say run all of the load instructions across all iterations before we run any of the sign instructions across all iterations. It turns out that style of lockstep execution is so useful, we're going to go ahead and do it. So we're going to actually go ahead and execute all of the loads across all of the iterations of the parallel for loop, and we're going to form that into a tensorized version of the slice. We go ahead now and we run all the iterations form of the sort of sign instruction. We have now a tensorized version of the sign. We keep doing this through all of the instructions in our original program, and we are able to generate a sort of tensorized version of our original CUDA kernels. Caveat, those original tensorized versions of the kernels are not necessarily the forms that you actually want to go ahead and run. So if we take that stencil kernel to begin with, I have those overlapping adds, or rather the overlapping loads that we multiply and add up together. That is not the convolution that I was promised and makes us run fast on the chip. But it turns out if you build a bunch of linear algebra optimizations on this high-level form, we can actually detect and turn this into a much better form of these tensor instructions. And we have a paper back at last year's UPSLA where we, in fact, even combined with egraphs to figure out the best search through this sort of linear algebra space to turn into the fastest form of the tensor instruction set. We can go ahead and run this, and we actually get very nice, pretty pictures. Not only do we get pretty pictures of the primal, but we also have the derivative. So here's actually, once again, computing the sensitivities now on, big, Earth models. And I forget which one is an atmosphere and which one is an ocean, but we have one of both. We ran this on very big sets of machines. We ran it on, thousands of GPUs on Alps. So we had like 9,000 GPUs, at 4 per node. We ran on the DOE machine, as well as, 8,000 of those Google TPUs that together claim to have, 46 exaflops, though with a big asterisk on the number of exaflops of FP8. Before we go ahead and say, did we take the single node version of the code and successfully run it on the big version, it doesn't really make sense to go run on 1,000 chips if you're 1,000 times slower on one chip. So we want to double check that we're still, even through all this crazy nonsense, having a relatively good version of our code. And at least for the single node CPU code, before all of the tensor optimizations on this climate model, it ran in 272 seconds. With all these tensor optimizations, we bring it down to 11.5 seconds. So it's even faster for the single core. So probably we'll get some good results when we go and change it to multi-core. So here we have the sort of weak scaling tests across GPUs for both the ocean and the atmosphere, respectively. What's shown here is the sort of time per grid point. In a weak scaling test like here, the basic idea is that you want to go ahead and have, you increase the resolution. So each GPU has the same number of grid points it needs to go ahead and compute. So the ideal scaling here is that it takes the same amount of time to go ahead and run each one of these individual pieces. So of course, in practice, it won't necessarily take the same amount of time. You might have some communication between individual GPUs and the likes. Fortunately for us here, we show that we are able to scale nearly perfectly. There are some blips and other stuff that I'll talk about a little bit later. We can also go ahead and run on the TPUs, like promised. At peak from this, we managed to go ahead and we used 97% of the overall TPU cluster, which itself contained 36 FP8 exaflops. In total, we used like almost 1.5 petabytes of HBM to go ahead and store the fields. There are some extra caveats here that we didn't fully fix in some distributed optimizations that I'll mention in a second. These chips have registers that are not just individual floats, but like a sort of like vector of like an 8 by 128 individual floats. Same weak scaling is relatively good. We do have like, that 8x there. On the one TPU, we get still the good sort of 40% plus of the runtime used in the computation, though again, we'd have some amount of an overhead. To give a little bit more detail on that, there's a lot of extra work that I won't have time to go into much detail on that is required to make this go ahead and run efficiently beyond just the linear algebra optimizations. As an example, we also had to build a whole host of distributed specific optimizations. So, if you're slicing all these overlapping pieces, you're sending data left, we really want to, as an example, do a common sub-expression elimination to, avoid sending the same data multiple times, as an example. Or another sort of example of this, if you slice off just the first element, because you're setting up a boundary condition, you're copying that to the sort of second guy, you're now taking a 100 by F32 tensor into a 1 by F32 tensor. And the sort of default way of doing this inside of something known as sharding here is say I have 10 devices for my 100 elements. I'm going to give 10 elements per each device. But now when I have one element for this intermediate tensor, how do I divide one element amongst 10 devices? You end up with like an all-to-all gather, and that's quite bad. It turns out we can do some notion of sort of like a communication fusion to get rid of it. And if we compare running these communication optimizations at the top right here versus not running these communication optimizations, we get an order of magnitude speed up. There's equally interesting questions here. How do we actually use the low precision arithmetic on side of this? If you're interested in the low precision parts, we have a couple of papers both at CGO last year as well as SC, and even later today, one of my students will be giving a talk at the eGraphs workshop on automatically leveraging low precision through arithmetic rewriting and the likes. So in total, Earth system models really have these 4 key challenges: scale, data, model, and code. The argument that I'm trying to at least make here is compilers are a promising route that we can automatically resolve all 4 of these challenges without the domain scientist needing to become an expert computer scientist. We demonstrate this in promising regimes for both differentiation with our tool enzyme as well as performance portability with our tool reactant. And both tools work generically across LVM/MLIR, all open source. There's plenty more problems than the ones that I sort of mentioned here that we've already started to explore with compilers that are extremely relevant to the Earth system and general community. And if you're interested, please reach out. Thank you so much.
So thanks so much for that talk. Loads of awesome stuff. I wondered about sort of the relationship, things like JAX, so the stable HLOs like compiling to TPUs. How would you compare that with an approach like JAX, which sounds roughly similar?
Yeah, so JAX also converts Python into that stable HLO representation. Caveat, by not being directly inside of the compiler, it presents some additional limitations through tracing. Like, you don't have direct access to for loops, you don't have mutation, so there's like the sort of the language level from there. Independent of the language level, there's also the question of like, how do you make sure that the performance from stable HLO to machine is actually fast? So all of these optimizations we did, say, for improving distributed performance, improving numeric performance, all of these equally apply to JAX code. So you can take your existing JAX or system model, take these extra optimizations with a flag I can recommend to you, and you should be able to fix a lot of these sort of things in that regime as well.
So your argument here is that a scientist shouldn't have to think about optimizing these things. They can write these Julia kernels more or less
Yeah, so the ideal here is that you write kernels in Julia or C++ or whatever else as you normally would have specified, which tells the compiler it's legal to run in parallel, and we want to convert this automatically into a form that is efficient to run across all of these devices. And it turns out that the efficiency part is hard, but fortunately that's exactly what compilers are good at doing.
Yeah. Maybe you can take one more question while.
Yeah, oh, sorry.